Hello and welcome back for another PureFX video here at the assembly line. My name is Björn Brotbeck and I'm working as an application chemist in the purification team of Büchi Labortechnik in Flaville headquarters. In the last video we have talked about peak width and peak shape and why they are so important. Today let's have a deeper look into the chromatographic parameter resolution and the solvents used in normal phase and reverse phase liquid chromatography. For this, let's go back to the laboratory. Welcome in the laboratory. Let me first introduce the chromatographic parameter resolution. The chromatographic parameter resolution is usually assessed by how completely two components are separated as they pass through the column. The resolution can be calculated with the following equation. And as you can see, the resolution is influenced by the efficiency, the selectivity, and the retention factor, or also well known as capacity factor. Here we can also see the influence of these three parameters graphically on the resolution. For good separation, a resolution of 1.5 is sufficient. Now, let's have a deeper look into the influence of these three parameters on the resolution. We will start with the retention factor. The retention factor describes the migration speed of your compounds through the column, regardless of the dimensions of your column and the flow rate. But the influence of the retention factor on the resolution is limited, as you can see in this figure here. Only at low values of the retention factor, the impact is high. High retention factors values increase only the retention time, but do not improve the separation. Next, efficiency. The efficiency is an indicator of peak broadening and indicates the separation stages. So if you want to improve your separation and therefore the efficiency, for example, you can reduce the particle size of your column or change, if you are using flash chromatography cartridges, change from irregular to spherical shaped particles. But as we can see in this equation, the influence of the efficiency on resolution is also limited, as the resolution only increases with the square root of the efficiency. Last but not least, selectivity. Selectivity has the highest impact on resolution, as you can see in this figure here. The selectivity is a measure of the separability of your compounds. So I recommend, if you want to improve your separation, at first optimize the selectivity. The selectivity itself is affected by the stationary phase and the mobile phase. Here, especially the solvent, pH, gradient, and the usage of buffers. But let's focus on the solvents, and we will start with the solvents used in reverse phase chromatography. So, the most commonly used organic solvents are methanol, ethanol, acetonitrile, and tetrahydrofuran, combined with water. These solvents have different properties, but let's discuss the most important ones for reverse phase chromatography. And we will start here with water. Water is the weakest solvent here in reverse phase chromatography due to its strong dipole character and ability to form hydrogen bondings. Methanol, on the other hand, is also a relatively weak solvent, as you can see here, due to its polar character and its ability to form hydrogen bondings with the sample and other methanol molecules. ACN is a strong organic solvent. It has the highest dipole character in this table here, from the organic solvents, but it can only form hydrogen bondings with other sample molecules and not with itself. Ethanol is another strong organic solvent due to its polar character and its ability to form hydrogen bondings with the sample and other ethanol molecules. In this table, THF is the strongest organic solvent due to its low dipole character and its ability to form only with the sample hydrogen bondings. You have also take care about the UV cutoff of each solvent. You may have to change your solvent if the UV signal of your sample is masked by the solvent. Another point is the costs. Water and methanol are really cheap solvents, but as you can see, they are weak, relatively weak solvents. On the other hand, ACN, ethanol, and THF are expensive, but on the other hand, they are strong solvents. But this is enough theory. Now, let's have a look on a practical example where we can see the different solvent strength on a separation example. Here we can see a separation of theobromine, theophylline, and caffeine using a C18 column with water and corresponding organic solvent as a mobile phase. And as we can see in the first chromatogram, with methanol, the separation is achieved in 7 minutes. If we substitute methanol with ethanol, we can reduce the runtime to less than 6 minutes. With ACN as an organic solvent, we can separate the 3 molecules in less than 5 minutes. As ethanol and ACN have completely different properties in terms of dipole character and hydrogen bonding acceptor-donor ability, it is not possible to make general statements about which solvent is preferable. It depends always on the application and must constantly be determined on an individual basis. With THF, it is impossible to separate the 3 compounds under the same run conditions due to its strong solvent strength. We must change the run conditions to achieve separation. Let's switch to another important topic, viscosity. Viscosity describes solvents' resistance to flow. Consequently, solvents with low viscosity are favored as they minimize the cartridge's back pressure. This figure describes the viscosity of organic solvents in combination with water. And as we can see, at around about 40 to 60% organic solvent amount, the highest viscosity are achieved. So, if we perform a separation, we usually use a gradient. And therefore, the amount of organic solvent will increase over time. But the viscosity of the mobile phase and therefore the back pressure will increase too. So in the worst case, not every application can carry it out at its optimal flow rate if you are using large cartridges, for example 3 or 5 kilograms. Otherwise, the maximum pressure of your cartridge will be exceeded. So let's switch to the normal phase and discuss some commonly used solvents. Commonly used solvents for normal phase are N-heptane, N-hexane, dichloromethane, ethyl acetate, and methanol. Water is included here in the table as it is the solvent with the highest solvent strength in normal phase chromatography. But we will start with N-heptane. Due to the non-polar properties, as heptane has no dipole character and hydrogen bonding ability, this solvent has a very weak solvent strength. N-hexane is only slightly stronger solvent than N-heptane, but hexane is also very unpolar and has no dipole character and hydrogen bonding ability. DCM is a moderate strong solvent due to its high dipole character. Ethyl acetate is a strong organic solvent due to its polar character and its ability to form hydrogen bondings with the sample, but not with itself. In this table, methanol is the strongest organic solvent due to its polar character and its ability to form hydrogen bondings with the sample and other methanol molecules. Very often, gradients of N-heptane or N-hexane with ethyl acetate or DCM with methanol are used. As you can see here, the costs. The weak solvents N-heptane and N-hexane are the most expensive solvents. As the solvent strength increases, they become cheaper. Compared to the reverse phase solvents, the solvents here in normal phase have significantly higher UV limits. So this must be taken into account so that the sample is not masked by your solvent. In contrast to reverse phase chromatography, the pressure in normal phase chromatography is not a problem, since the viscosities are very low. Now we have a look at an example where we can see the influence of different solvent strength on a separation example. In our separation example, we show a separation of toluene, the octyl phthalate, the propyl phthalate, and the methyl phthalate in an isocratic run. With an N-heptane ethyl acetate mixture, the separation of the four components is well possible. But, however, the separation takes about 7.5 minutes. The substitution of N-heptane with N-hexane reduces the runtime to about 4.5 minutes due to the higher solvent strength. But as you can see, toluene and the octyl phthalate are not completely separated. A mixture of DCM and methanol cannot separate the mixture due to its high polarity. Depending on the application, the solvent strength must always be taken into account, as this significantly influences the runtime and the separation. I hope I was able to give you a good insight to the chromatographic parameter resolution and the influence of normal phase and reverse phase chromatography on the separation. In the next video, we will talk about the other parameter which affects the selectivity, the stationary phase. Now, in every case you need help for your separation, please contact us at application@buchi.com. See you. Bye.